Okay guys, in this video we're going to introduce gases and how they work in our universe, alright? So to do that, we first need to talk about what are gases, okay? If you go back to kind of your middle school definition, you talked about how gases don't have a set volume, or maybe they say they don't have a set shape to them, which is true, but we really want to define that a little bit better than just that idea, okay? So let's talk about what gases can do. Gases are able to expand to fill any space, okay? So if you put 1,000 particles into a container, they will expand and fill that container freely. Okay, so they're able to move around freely and do that. They are compressible, which means you can actually compress them together, or you actually can expand them apart. Okay, so they don't have a set volume, which means they can be compressed. Okay, that's different than liquids and solids, which cannot be compressed. And then they are free to move with no attractive forces. Okay. What that means for us is when you have gases moving around, they're actually independent of IMF. Remember, IMF is intermolecular forces. So we have all these forces out there in our universe that hold solids and liquids together. It keeps them from separating. It allows liquids to flow back and forth. It keeps solids in their rigid structure. Well, gases are so far apart, they're moving so fast that they actually break free of this IMF, or these intermolecular forces. So gases kind of act independent of these forces. Okay. Now, all these properties of gases are based off something called the kinetic molecular theory. Okay, so it's a theory, so it's an explanation. So we're explaining how molecules work based off of their kinetic energy. So things we want to look at. Gases are dependent on 4 different variables. Okay, so when we're working with gases, we always have to keep in mind 4 different things. They are pressure, temperature, amount, and volume. Okay, we'll talk about defining all these things and making sure you're comfortable with those. Volume you should be pretty comfortable with already. Amount is new to us, but pretty comfortable. That's the mole. So how many moles of it we have. Yes, the mole doesn't go away. Temperature we've talked about a little bit. We're going to add to it in this unit, and then we're going to definitely define pressure for everybody. Okay. Notice one thing. These variables, we have amounts and volumes and temperatures and pressures, but we do not talk about this type of substance we have. So we do not care if it's oxygen or nitrogen or carbon dioxide or hydrogen. We don't care what gas it is. So the type really doesn't matter here. All gases act the same, basing off their basic laws. Okay, so that's kind of nice, is that we don't really need to have different rules or different parameters based off of the different gases. They all act identical to each other. Okay, so let's dive into this idea of the kinetic molecular theory. All right, first thing. Molecules of a gas move rapidly in constant linear motion. Okay, so they're moving at speeds of thousands of meters per second in linear motion. So they go in straight lines. Okay, they can change direction when they contact another molecule or the wall of a container. Now, what I always tell students is think of a game of billiards in a 2-dimensional format, where if you have the cue balls and the balls on the table playing pool, and you start throwing them around across the table. I know as a kid I did this. I know my kids do this. So you get all the balls out there, and you just start throwing them around at each other, and they bounce off the walls. They bounce everywhere. That's kind of like how gases move. Okay, so they're just bouncing off the walls, that kind of stuff, moving in straight paths. That's all they really are doing. Okay, until they hit something, they move in a straight line. Okay, so that's how gases move. They're constantly moving straight paths, and they're constantly colliding with each other, and they're colliding with the container walls. Okay, because of that, we end up building pressure from that, because as collisions happen, that creates pressure. Okay, now other part of this law that's very important to us is we're going to assume that the gases act as ideal gases. Okay, so in our universe we have real gases that we really deal with under real circumstances. However, for the math to be simplified, we sometimes take a few variables out, and it makes it easier for us to work with it. When we do that, we call the gases that we work with mathematically ideal gases. Okay. Now, lucky thing is, under most temperatures and pressures, real gases and ideal gases work identically to each other. So it's actually a really good approximation for us. Okay. So let's talk a little bit more about ideal gases and kind of what they are and how they work. Okay. So first thing. Collision between the molecules are completely elastic. Okay, so in the world of physics, when we talk about elastic collisions, what we're talking about are collisions that do not lose any energy. All right, that's pretty rare in our universe. Most collisions do lose a little bit of energy. For ideal gases, though, we're going to ignore those small drops of energy that go out to heat and friction and that kind of stuff. Okay, we don't lose it; it's not gone or destroyed. It gets lost to like heat buildup and those kind of things. Okay. So we're going to ignore that tiny amount of energy that possibly could get lost when they collide. Okay. Now, the energy we're talking about here is kinetic energy. Okay. So what we're saying is that we're not going to have to factor in changes from kinetic energy into thermal energy in any of our math. That's what we're basically saying here. Second thing, no attractive forces between molecules of a gas. Okay, we've already kind of talked about that. But the reason behind why this is because our particles are so far apart, they're moving so fast, we can ignore those intermolecular forces. Okay, they do exist, but they're so incredibly weak comparative to the speeds at which they're moving, how far apart they are, that they really have no effect on gases at all. And then last but not least, the particle itself has no volume. Okay, that's a really kind of a tough concept sometimes for students to understand, and it might help you to think of it as a point on a grid system. That's all it is. Okay, so the particle itself has no volume. Okay, so if you start to look at the idea of gases spaced out in long distances from each other, the size of the gas particle itself doesn't really matter because the distance from them are so great. Okay, so to give you kind of a comparison, if we talk about you want to go on a trip to, let's say you want to go down to Florida, okay? And you want to say, how far is it to Florida, okay? Usually when people search that stuff on Google and they want to say, how far is it down to drive to Florida, if you're going to drive down to Florida, maybe you're going to go down to, I don't know, Tampa Bay or something like that, Florida. So you go into there, you might type in Eagan, Minnesota, you might type in Tampa Bay, Florida, and hit enter, and it's going to give you a map of the distances, okay? Now, you're not going to add in the distance it takes you to walk from your room of your house out to your car and pull out of your driveway, are you? Okay? Because that distance is negligible. It's kind of not worth anything, really, okay? Same idea when it comes to planets in solar systems. We say that we are 93 million miles away from the sun, okay? So, yeah, we are, but do we add in the distance of the diameter or the radius of our planet to that distance? No, we don't add that in because it's negligible. It doesn't really matter. So the size of our planet in comparison to how far away from the sun really doesn't affect the data on what we talk about. Same thing here. The size of the itty bitty tiny little gas particle really has no bearing on the distances they are between each other. So we kind of ignore their volume that's there. Okay. And then last but not least, of course, keep in mind that real gases do act ideally under normal temps and pressures. And normal in our world is our world. It's our world and hotter, actually, is what we think about. We're kind of the bottom end of it, but normal temperatures, normal pressures is our universe, that we work in here on our planet. Okay? So that keep in mind, we will talk about how these things diverge away from each other later on in the unit. So what happens when they aren't ideal anymore. All right?